Welcome, everyone. Hello and good morning. Welcome to our second UW Reality Lab lecture of 2023. And today we're being joined by Mark Billinghurst, who I know it's early in the morning for some of you, but it's certainly earlier for him being in Australia right now. A little background about Mark. So he actually did his PhD at UW at the HIT Lab back with Linda Shapiro and Tom Furness. He's gone on to publish a myriad of publications in augmented and virtual reality research, specifically focusing on new forms of interaction methods, some really cool stuff with ubiquitous computing and different types of input devices, empathic computing as well, and remote collaboration and looking at how people can actually interact through these technologies. Mark is now the Director of Empathic Computing at the University of South Australia, as well as a professor at the University of Auckland. So today's going to be telling us about empathic computing and his research. So that intro said, I'm going to hand it over to Mark.
Great, thank you very much. It's a pleasure to be here. I'm sorry I couldn't be there in person. I always love visiting Seattle. So, okay, well, thank you so much for having me. As I was introduced, I'm Mark Billinghurst. I am a professor at the University of Auckland, and I also have a joint position at the University of South Australia. And I'm going to talk about empathic computing, new directions for collaborative XR. But to start off with, I wanted to let you know again, many years ago, I was where many of you were. I was actually a student at the University of Washington. Here's an early picture of me having a barbecue at one of the parks around Washington. And so in the early mid to late 90s, I was a PhD student there. And I'm really appreciative to the University of Washington because it gave me my opportunity to have my first VR experience. So here's the VR gear we used at the time, about $250,000 of technology. And we had a budget of 1,500 polygons for building our VR environments. So very, very small polygon budget compared to what you can do today. My PhD research was really on collaborative systems. In fact, in my PhD, I built some of the first collaborative augmented reality systems and explored how to do that, and graduated in 2001. So it's been over 20 years now. So what I'm going to talk about today is communication. And of course, you know, communication is very, very important to all of us. The Brazilian philosopher Paulo Freire says that only through communication can human meaning hold life. And because of that, we've developed lots of technologies over the last tens of thousands of years for communication, going back to cave paintings, to, you know, carrier pigeons, telephone, the television, and of course today we have these multiple channels of communication technology. But probably like the most of you, over the last couple of years, I've spent a lot of time on Zoom and looking at video conferencing and communicating. And of course, today we have a lot of different teleconferencing devices, but we pretty much discovered that using those devices is very different from having a face-to-face conversation. You know, and face-to-face, we have a very wide variety of communication cues that are used, a mixture of audio cues and visual cues, but especially cues relating to the environment around us. And you can see here's a picture of some architects who are talking about a building they're going to build, and they're using a model of the building and plans of the building as well. And one thing you'll notice in this picture is that the task space, the building they're talking about and the task they're doing, is a subset of the communication space. And when we introduce technology into the mix, sometimes that changes. So of course, in face-to-face communication, we have a wide range of channels of audio, visual, and environmental cues together. But when we start communicating over distance, that changes. You can see, for example, here's some people talking face-to-face, and they're looking at this monitor. And you know, the task space now is on the monitor, and the communication space is separate from that. It's very hard to see everybody else's faces while you're looking at the monitor. And the same thing happens in remote conferencing. Here's a typical video conferencing setup with some people collaborating with some colleagues around chemistry. They've got a large screen showing the remote people's faces, and then also a second screen showing their molecule they're talking about. And once again, when we start doing that, we degrade the audio, visual, environmental cues. And in this setup here, you know, the task space is separate again from that communication space. So you have this kind of communication seam that exists between them. So with current technology, there's a number of limitations. You know, it's a lack of spatial cues. When you're talking to people on your phone, they kind of blend with the background. You have poor communication cues, limited ability to communicate gaze, gesture, nonverbal communication. and this introduction of this artificial seam, like I just talked about, between the physical and digital space. So when I started doing my PhD, I reflected on some movies that I was really excited about, and thought about how they envisioned communication in the future. And in particular, the Star Wars movie. This is the third, or I guess it's the sixth movie now. So here they all are sitting around talking about how they're going to destroy the second Death Star, and you can see they have this virtual image of the Death Star floating in space in front of this conferencing room. So this is a simple example of augmented reality, and you see with augmented reality, when you've got several people talking across a table, then again you can have that task space being restored as a subset of the communication space. And so during my PhD, we actually tried to make that real. So this is a project from the late 1990s called Shared Space, and we built the first face-to-face collaborative AR system where you could have people standing around a table, seeing each other in the real world and seeing AR content on the table in front of them. And that content was anchored onto real tangible objects. So this is a video of the system working. You can see this is through the headset. When or my friend is looking at this card here, you can see this virtual character appearing on this card, and it appears anchored on the real world. In this case, we're using video see-through AR systems that we developed. So this is a graphics content superimposed over video of the real world. The most important thing, though, is that, as you can see across the table, when she lifts her head up a little bit, she can see her collaborator across the table with her. And so she can see his face and she can see his hands, and they can communicate using nonverbal cues as they would in normal face-to-face collaboration. And in this case, they're playing a simple game. They're trying to match cards together that belong with each other, and when they get the right card together, a simple interaction happens. So you can see this is a witch's broom, and there's an alien on the other card, and they don't match up, so nothing happens. Now, because the AR content is anchored in the real world, then of course when she sees the alien's face, he sees the alien from the background, and the interaction is as simple as interacting with real objects. And so when he turns over this little UFO, of course, there is a match there. And when he puts them together, there'll be a simple interaction happening. So you see this little interaction happening as the alien flying around the Earth. So that was more than 20 years ago. And in my PhD, we also explored how we could use the technology for connecting at a distance. And so, people nowadays are using AR and VR to explore connection at distance by restoring spatial cues and steering nonverbal cues, and also creating these shared communication spaces. And again, referring back to Star Wars, there's a lot of inspiration in Star Wars about how you had these kind of virtual holograms of people appearing in your real space to be able to connect with you. So over 20 years, I've done research in the space as well, again, starting at my time at University of Washington and looking at how we can create video textures of people from the real world into your space. So some of the early experience we did was some of the first shared VR experiences, and then we built this AR conferencing system. And the idea was to bring video conferencing into the real world and be able to let people have name cards, and when they turn the name card over, they would see a video of a person in front of them. So you can see this in this video here. What you'll see is this person, he's, sorry, let's turn the video audio up a little bit. He's doing a Lego construction task, but he's getting stuck. So he's going to call the Lego helpline, so his name card. When he turns the name card over, he will see a virtual video of a remote person, and she starts giving him help. And in this case, we're sharing video from what he's seeing to her, so she can see what he's seeing and can help him, and they can show him objects to see as well. The key thing, though, is that instead of the person being on a monitor or on a device, they appear in your real world as part of your real workspace. So in the studies we did, we created a very high sense of social presence because the person was right there in your workspace. One thing you'll notice, though, is that person appears as a flat video texture. So if he had turned the card sideways, she would have disappeared. So a year or so later, we developed a video conferencing system that used multiple camera views and was able to generate synthetic camera views from real cameras in between the real camera position. So I'll show a video of this working. in this video, you'll see virtual characters that look like they're 3D. So you can see here a person being captured in a green screen, and in that environment, there's 16 cameras surrounding him. And so we can generate a synthetic camera view from anywhere between those real camera positions. And so now we can create this illusion. You can see here, it looks like a pair of dancers dancing life-size on the roof of a building. Actually, there's only one dancer dancing, but because it's AR, we can make a copy of her and make 2 dancers appearing there. And then we could use it in video conferencing as well. This was the same time as the Matrix movie came out, so we could do bullet time effects. We could freeze frame. We could look around a person. And now you can see it really looks like there's a 3D model floating in space. Although actually, in this case, it was kind of an illusion. It was actually, all those images were all still 2D images, but because we're able to generate multiple 2D images from different views, we could, as you move the camera, the images that were being created look like it was 3D. And again, this was 20 years ago. So since that time, there's been a huge amount of work in this effort. We've got companies like Microsoft with Outspace VR and Meta with their Horizon and Spaces, looking at new types of collaborative VR, social VR experiences. And then companies like Magic Leap building avatar chat environments. And Microsoft now is developing the Microsoft Mesh that kind of pulls all this together to create a framework for remote and face-to-face collaboration. Which brings us to the metaverse. Of course, over the last year or two, that's been popularized primarily through Meta, who changed their name because they like to come up with the name so much. And they've been pushing this idea of social VR. If you do a Google search on the metaverse, it's become hugely popular since October 2020, and you can see the blue lines there showing the search volume on Meta versus the red lines on virtual reality. And actually, if you look at the number of publications on Scopus published about the metaverse, there's this huge spike appearing. I think actually this is out of date. If I looked again yesterday, in 2022, there were over 1,000 publications that had the name metaverse in their abstract or keywords, compared to just 50 the year before. And I made a joke a few months ago that if it continued this trend, pretty much every paper in computer science being published in the year 2025 will have to have the metaverse in the title or in the abstract somewhere. So it's become very popular. But if you go back to Neil Stephenson's vision of what the metaverse was, it is actually a little bit different from what Mark Zuckerberg and other people are pushing now. So in his book Snow Crash, and if you haven't read it, I highly recommend you reading it, he talked about how the metaverse is a convergence of the virtually enhanced physical reality and physically persistent virtual space. So there's really these 4 key this taxonomy you can build with these 2 axes, one axis between augmentation and simulation, and one between external and intimate technologies. And they lead to these 4 quadrants. So for example, augmented reality is an example of augmentation. We're enhancing the real world and it's externally focused. And virtual reality is an intimate technology. It's enhancing your personal experience and involves simulation. So it exists in the other quadrant. The pieces you may not be so familiar with is on the top right-hand corner, which is life logging, and the bottom left-hand corner, which is mirror worlds. And so mirror worlds really refers to creating a copy of your real environment. The Google Street View's a simple example of that. And life logging is basically being able to record your personal physiological cues and capturing your personal experience. And Apple Watch with their EEG recording and ECG recording is a simple example of that. So the metaverse is really popular, but many people who are doing research in the metaverse are really only thinking about that social VR space. And so in our lab and our work, we're trying to broaden that. And it turns out if you look at the connections across these boundaries, you can create a huge amounts of research opportunities. And so you can imagine research when you're trying to combine life logging to VR, so bring real world reactions to VR, or AR to life logging, where you might be able to record your motion using your watch or your phone. And when you go out in the real world, you can see the paths you've walked in the previous day, for example. So I want to talk about a few examples of some of these and relate them back to the topic of empathic computing. So when you start crossing between these boundaries, you can do some quite interesting research. One example is combining augmented reality with measuring nonverbal and physiological cues. And so a few years ago, we developed a system called the empathy glasses. And the idea was to be able to capture and share those cues in face-to-face communication that you don't have normally in remote communication, so eye gaze and face expression. So we combined 3 technologies together, eye tracking, AR glasses, and Effectiveware, which was a frame to measure your face expression. And we put them all together and we developed and included that into a remote collaboration system. So on the right-hand side here, you can see what the person's seeing in their AR display. Most importantly, though, there's this red and green dots. I'm not sure if you can see my cursor, but that green dot there, this is a remote person they're collaborating with. This is their pointer that they're showing to their space, so giving them instruction. And then more importantly is the red dot above that. And the red dot is their eye gaze. So the remote person, when they're using this technology, can know where the person's looking and can have that eye gaze information. So this is a video of the system working. And what you'll see here is a person doing a block assembly task, and he's been guided by this remote person on the laptop. So the remote person is able to talk him through the task, and he indicates using that green pointer, but he can see if the person's paying attention or not, because the eye gaze follows him. So it's a really important implicit communication cue. And we also share the heart rate information and the face expression you can see on the bottom. So when the person finishes the task, he smiles, and that's communicated. What we found by doing this is by sharing those gaze cues and the pointing cue, people felt a lot more socially connected. Oh, this is how we did that face expression sharing by using photosensors to capture the distance to your face muscles. So that really created a strong sense of social connection. And you can do the same thing and similar thing in VR. So if you look at combining VR to life logging, we developed a system where you could measure somebody's emotions in VR using the heart rate and sensing and GSR, and then we could share that with a remote person. So the idea was somebody's in VR, having a VR experience. You can have a second person who's an observer who is in that same person's virtual body. So they're sharing the same body, but you share the heart rate of one person with the other person. And by sharing that heart rate information, we felt we could create a stronger sense of connection. And we tested that in 2 different VR environments. One is a butterfly world, which is very peaceful and calm. And the second was a zombie game where you had zombies attacking you, and you got very scared, and you can see the heart rate there.
In this research, we explore the effects of sharing physiological states of players in collaborative virtual reality gameplay. Our goal is to improve and enhance users' empathy among collaborators, especially in a remote setting using advanced computer interfaces. To support this study, we developed a collaborative VR framework which shares the player's position and heart rate to the observer in a virtual environment. The observers view the game from the player's position, but can rotate their head freely to look around. The player's heart rate is measured by a biometric glove. The measured heart rate is shared with the observer using both visual and audio cues. We developed 2 games based on this framework. The first game provides a calm and pleasing experience where the player catches butterflies while surrounded by nature. The second game presents a scary and stressful situation where the player tries to survive zombie attacks. We conducted a study to learn the effects of displaying the player's heart rate to the observer. From the insights gathered in this study, we present a set of guidelines for designing collaborative VR experiences.
So for that study that was published at CHI conference, I think 3 or 4 years ago, we found that by sharing the heart rate information, the remote person, when the person who's playing the game started getting excited, then the arousal and valence scores from the remote person also went up as well, and they started feeling similar emotions. You can also look at how you can combine AR and VR and the mirror world elements together. And so I showed you the example from the empathy glasses of having a camera on your head and sharing that with a remote person. That's being very commonly done now in remote collaborative AR systems. One of the challenges, though, is the person who's remote only gets to see the real world through the camera of the person who's wearing it. And so they only get to see a small view into the real world. So we want to overcome that limitation, and we want to be able to create a virtual copy of that person's whole surroundings. And so a simple way we did that is, instead of having a normal camera on the person's head, we would share a 360 video view, and we'd live stream that just to a remote person who's in VR. And then the person who's in VR, we can capture their hand gestures and we can share that back to the person in AR display. So you can see a video of that working here, and that allows the person who's in VR to feel like they're in the same environment as the person who's in AR. So let me just play the video here. So this is work done with a power company, and you can see here The person's looking at this quite complicated power control panel. He's wearing the Microsoft HoloLens in a 360 video, and he's live streaming the video to the remote person who's viewing it inside VR. So this is what the person sees in the real world. He sees these kind of ghost hands appearing over his view and drawing on the real world. And of course, the remote person can talk to him as well, so they can then communicate about how to operate the system. That green square there shows where the remote person is looking, because now the person can look wherever they like. This is the remote person. And as they look around, they can see wherever they want in this 360 video of the real world. So in many ways, they feel like they're standing inside that local worker's real body. So they can look around and they can draw on the real world and share annotations. And we found this would be a very effective way to communicate. One of the challenges with this, though, is, of course, the person who's watching 360 video is just watching video. And so you don't have any 3D geometry. You can't walk through the space. You don't get any sense of the spatial relations with objects. So in the latest version of the software, we've looked at how we can combine multiple depth sensing cameras together, and we can create a live 3D point cloud that we fuse together to create a live scene of the real world. So in this video here, you can see on the left-hand side a God's eye view of my lab, the right-hand side the first-person perspective. And this is a live 3D model. So when my student walks into the space in a second, you'll see them coming to the space. And now I can walk through that. The VR user can walk through the model and experience it as well. There's lots of blue space here. The blue space is where the sensors can't see, so behind the person, underneath the table. And we can use this for doing scene capture and sharing. So if we take those depth sensing cameras and surround a table, for example, we can capture whatever is on the table and we can live stream it to a remote person in VR, and they can be guided. They can guide the local worker in AR. So in this picture, you see a remote expert wearing a VR display. On the right-hand side, you can see the local worker wearing the AR display. This is what it looks like. On the left-hand side, you can see the AR view. This hand gesture is saying, pick up that yellow object. Then the person picks up the object. You can see it's being moved from the right-hand side VR view, and then they can align it in the real world following the guides from the person in AR. So this is all happening in real time. So the person in VR gets a real-time update of the space and really feels like they're part of there. So you can see that we've evolved from just sharing 2D views of the environment to sharing 360 video and now 3D content. And the hope is that in sometime in the near future, there'll be a small handheld device you can carry into the real world, and it'll be able to live stream your 3D environment to remote people for better collaboration. There's some trade-offs, though. With the 360 video, you have high quality visuals, but of course, very poor spatial representation. With 3D reconstruction, you can have very good quality 3D space, but the visual quality is quite poor. So in a follow-on project, we looked at how you could flip between them. So you could basically have somebody who's in a 3D real environment, and they can use a 360 camera to share their real environment, as well as having a 3D model of the environment. And the VR user can flip between being in the VR model, 3D model, or in a 360 view. I don't have time to play the video, but I can share that with you as you're interested later. So the last thing I want to talk about is being able to combine AR and VR and sensor input together. So can you use AR, VR viewing with physiological cues as well? And there are many opportunities of research in that space. One of the more interesting things we've done is a project called the Neural Drum. And the idea was to create a AR, VR game. It was a collaborative drumming experience. But while people were drumming, you'd measure their brain activity using EEG electrodes, and you'd look for moments of when the brain activity was synchronized. And when that happens, you would increase the fidelity of the VR experience. So we built a system where we had some drumsticks with Vive trackers on them. We had some EEG electrodes connected up to the OpenBCI hardware and software framework to measure brain activity. And then we created this. I'll show you the video here. So let me just turn the video quickly.
Neural Drum is a VR drumming experience that allows two players to drum together while their brain signals are simultaneously measured. At first, you can set some daily objects on a table to use as drums. The player will use two drumming sticks to play the game. both of the players will wear an EEG capturing hardware to get their brain signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neural synchronicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between two players is low, the camera will be more clear to do so, whereas when synchronization is high, the vision becomes more obscured with each point cloud eliciting higher particle effects. We logged and analyzed the user's brain signals, as well as had them answer a subjective questionnaire regarding their perception of synchronicity with their partner and the overall experience during a pilot study. We discussed design implications to further improve NeuralDrum in our paper.
So the basic idea was you start drumming, and when you start drumming, you have this kind of mixed reality view. You can see your partner in the real world drumming with you. But as you get in phase, then that fades away into a more VR view, and we introduce more visual effects like particles and other fireworks and things like that. And what we found that with good players, as they started drumming, they had more moments of synchronization, and they felt more connected. So one person, for example, we showed this at the SIGGRAPH Asia conference, they said it's really interesting. I actually felt like my body was being exchanged with my partner. So a really strong sense of connection. So a common theme with some of this research is when you interact through AR or VR, oftentimes you're represented by a virtual avatar. So you have these real characters in black and these virtual avatars that are representing you in blue and red. And so because you're represented by a virtual avatar, you can do a lot of things you can't do in the real world. And I've shown you some of them already. You can do things like show virtual cues, you can do scene caption, things like that. But there are some other interesting things you can do as well. And so I want to talk a little bit about that. One of them is that you could show some virtual communication cues that you don't normally have in the real world. For example, in this case, we did a collaboration between an AR and VR user. And, on the left-hand side there, you can see this pink avatar head and these hands representing them. But we wanted to be able to show where the person was looking. And in the real world, you can only tell that where you can see somebody's face. But in AR and VR, you can add some other additional cues. And so in this case, we added these virtual view frustum. And so we could see this view frustum coming out of the person's face. And that meant that I didn't need to look at the person's face anymore to know where they were looking. So we developed a system where we had one person in the real world performing a task, and then we had a person in a VR copy of that same real environment, but helping them with that task and being represented by the avatars, and you can see that here. So here's the environment that we've got. This is the AR view. You can see the virtual avatar with these green or blue lines coming out of their face. And then this is the VR view, again with that view frustum coming out of their face. And now we're going to look around the environment trying to find these blocks, and I can see where the person's looking, even though I can't see their face. You can see the view frustum there, and as they move closer to the block, their face comes into view. And we did a task where you had to try and find blocks with numbers and letters on them, and the AR person could only see numbers and the VR person only letters, so they had to communicate together. And what we found was that by sharing that view frustum and having those gaze cues, we were able to create a stronger sense of social connection. We also changed communication patterns. People didn't even need to ask what they were looking at anymore because they could see what they're looking at. And there was a higher sense of co-presence. Once you've got a copy of somebody's body and you're in an AR/VR situation, you don't necessarily have to remain in the same body scale as you are in the real world. So you can do some interesting things with multi-scale collaboration, changing somebody's body scale to make them bigger or smaller. And so in this video here on the left-hand side, you can see the VR view of somebody in VR, the right-hand side, the AR view, and the person in VR is dropping blocks down using a little interface there. But they just make themselves really big now, and now they're 4 times as large. And on the AR view, this giant head looking down at you. And now you get a more God's eye perspective. You could imagine this might be useful in some sort of command and control application where the police chief wants to look at what all the people are doing in a building and makes himself really big so they can see virtual copies of their officers working around the building. And then if I wanted to, I can also make myself really small and explore elements of the world I couldn't see in the real world because I'm too large. So now the person in VR has gone back to 1:1 scale. Now they made themselves much smaller, and they can now look up and see the AR user as a giant head looking down at them. So this is one example of how you can change body size and scale to alter collaboration. This is another example. In this case, we've got a remote person helping somebody in AR do a PC repair task, but you'll see that the person in the real world is holding the remote person in their hands as a little avatar, and they can move them around, and they share the live camera view from their perspective, so they get the feeling they're actually holding the other person in their hand. And then as the person turns around and looks, the AR person remotely looks around, you can see the little view flash on the person looking around as well. So that person now can help them perform this physical task. We've also done some, and of course, I've shown some examples of being able to share a person's view, being able to snap into the same view. We've done some research on sharing different types of communication cues as well. If you can share gaze and gesture, how should that be done? For example, do you want to share a remote pointer or a full hand gesture? And we looked at what type of gesture cues should be shared. It turns out the gesture cues you share really depend on the task. So in this experiment, we looked at doing a Lego assembly, a tangram task, or a origami folding task. And with the Lego assembly, having a 3D hand shape proved really beneficial because you could use gestures to show how the objects were being manipulated. Whereas with a tangram, which is really 2D task, just having a pointer was sufficient to do the task. And we've done some work on sharing gaze cues. So many of you may have used AR or VR experiences where you've got a gaze line, and Magic Leap, and now with HoloLens 2, they've got eye tracking in their displays. So there's a big question about how do you represent that eye gaze, and it's quite common to have a virtual gaze line or a virtual gaze pointer being appeared. But what we did in this case is looked at how we could customize the gaze representation depending on how people's eyes were behaving. And so, people will move their eyes in many different ways, subconsciously scanning the scene, or they'll pause to focus on a point of interest, or they'll read and they have reading motion. But in most current systems, they're all represented by the same gaze reticle or gaze cue. In our system, we change the gaze representation depending upon how people's eyes are moving. So, if you were browsing and scanning around, you would see this blue gaze line and gaze circles. If you're focusing on a point, that would change to yellow. When both people focus on the same point, it would change to green, and there will be this heat map created of your gaze views as well. So you can see a video of that here. When the person's browsing around on the top left, you can see this blue line moving around. When they focus and pause, it turns to yellow. And then when both people look at the same location, that turns to green. And we did a collaboration with one person in AR. You can see the AR view here, and a person in VR being able to see that person as a virtual avatar. The VR user was seeing a 360 video of the surroundings, again, like I showed before, and they had to kind of solve a puzzle together, and they're looking around and gazing around to see the puzzle options as well. And then most recently, we've done some interesting work about how you could separate out the communication cues. So right now, of course, when you're in social VR, people look at how you can have an avatar that represents your gaze or gesture or nonverbal cues. But what happens when you can't see your avatar? So you can see here, you've got these two people collaborating in VR on the left, but on the right-hand side, the collaborators now is out of view. They're standing behind you. You can't see them anymore. So how do you know where they're pointing at or looking at? And so we had this idea where we could separate out the communication cues from the avatar itself. And so when you can't see the life-size avatar representing your colleague, we can create a little miniature avatar that always appears in your view, exhibiting the same communication behaviors. So that was this idea of mini-me. So here you can see a life-size AR avatar, and when the lady turns away from that avatar, this little miniature avatar appears and pointing to the same location in the real world and showing the same communication cues. And this is really important, especially for AR experiences, because with most augmented reality displays, they have quite narrow field of view. And so if you're trying to look at AR content on a table, you can't really see the avatar of your remote collaborator at the same time because the field of view is too narrow. So this little video shows that. So here's a AR with limited field of view. I'm looking at this content on the table, there's some AR tags on the content, and then there's the avatar there, but I can't see both at the same time. So with our technology, when you look away from the avatar, you see this little miniature guy appearing, and he points at the same location in the real world as the person in the remote collaborator is pointing at. So you can see here that situation where one person's behind the other. The person in VR is pointing at that T box on the table, on the shelves there, and then a little miniature avatar appears of them in the person's view pointing at the same T box. And how that happens is that when I can no longer see the life-size avatar of a remote collaborator, the little miniature person appears and points into the real world. So we did some experiences like that, and we found that when people had this mini-me, they could collaborate 20% faster, they had a higher sense of presence, and we asked them about their preference about using an interface with that and without that. And we had 2 different tasks, and in one task, people had a 60% preference, the second task, 75% preference. One user, for example, said, I felt like I was talking to my partner, even when they weren't in view. So there's a lot of interesting research you can do when you think about how you can modify people's avatars or represent them different ways. And so I kind of want to bring this to a little conclusion where what I've shown you today is how you can take elements from that metaverse taxonomy, and rather than just focusing on social VR, you can combine them together and look at research opportunities across different elements. And that brings me to the last point I want to talk about, which is empathic computing. So over the last few decades, there's been lots of trends happening in communication technologies. And I'd say 3 trends happening now. One is towards experience capture. So rather than just having Zoom calls where you can see people's faces, people are strapping cameras onto their bodies and putting LiDAR sensors into their iPads, which allow you to capture your real environment and share that. So you can now have experience capture and share your surrounds. We've gone from having dial-up modems to gigabit connections, and that means now we can have very high bandwidth communication, more natural communication. We can have virtual characters and share HD video. And the third trend is towards implicit understanding. So this means we're building systems now that can use cameras to look at our faces and recognize our emotions and face expressions. We can track our bodies, recognize using behavior. We can even wear on our heads, EEG sensors to recognize our brain activity. So computers now have a more capable of implicit understanding, recognizing our behaviors and emotions. So those 3 things together, natural collaboration, experience capture, implicit understanding, really combine in what you might call empathic computing. So most of you, of course, know what empathy is. This is Alfred Adler's famous quote, psychologist, saying empathy is seeing with the eyes of another, listening with the ears of another, and feeling with the heart of another. So the main idea of empathic computing is, can we develop systems that allow us to share what we're seeing, hearing, and feeling with others? And so the 3 key elements of empathic systems is understanding, so emotion recognition, using physiological sensors and other things, experiencing, so being able to share content or environments with others, and VR is really great for that, and then sharing in real time your experience, sharing communication cues, and AR is really good for that. So we have these 3 elements, and people have done research in these areas before, and understanding, experience, and sharing. But in the third space of sharing systems that help better share your experience with others, this is a much newer topic, and that's where my lab is focusing. So just give you a bit of context, being able to understand people's emotions, that was popularized by Ross Picard and others with the field of affective computing, and it's in that field, they're building systems that recognize and share emotion. But in many cases, these systems are single user systems. A good example of that is Junior Reikimoto's work from 2 years ago or 3 years ago about appliances that make you happy. And the idea of this work is that you could build into your everyday appliances the ability to recognize your emotion and then to have them make you happy. So I'll have a short video of that. Let me just play the video here. And in this video, fast forward a little bit. So this is premised on the idea from the psychologist William James, is that we don't laugh because we're happy because we laugh.
And philosopher said, we don't laugh.
So if we can force people to act happy, we might make them feel happier. So they built this system called the happiness counter. And this is a little camera combined with a LED display that shows whether you're smiling or not. And then he embedded this in different everyday technologies. So here's a mirror, and the lady is standing in front of the mirror. And when she smiles, then this smiling icon shows up as well. And so he did a very nice job of hacking this together. So he took a Sony CyberShot camera, and the CyberShot camera already has a smile detector built into it, and an icon lights on the back when the people's smile is detected. And so he just put a light sensor where that icon was, and then combined it to this LED array, and then he built a smile sensor. So that was very, very quick hack. And then, as I said, embedded this in different technologies. So you can see in a second. Okay. Here's that lady in front of the mirror again. She's not smiling, so it's showing a frowning face. It's trying to remind her to smile. And so now she smiles and the icon goes away. But he wanted to be a bit more assertive than this, so he actually put this into other devices, and so in particular into their fridge. And so he created a fridge that had a magnetic lock on the door. So you can still open the door of the fridge, but you have to pull really hard to unlock the fridge. But then you connect the magnetic lock to the smile detector. And so when you smile at the fridge, it turns the lock off and makes it really easy to unlock the fridge and open the fridge. So you can see there. So basically forcing people to smile if they want to get food, which is, I guess, one way to do experiments. And like any good HCI researcher, he decided to test this in a user study. So in a second, you'll see a study he did, a field test. So he tried to find a grumpy old man in Tokyo, and fitted the system to the man's fridge. So here's this man here. Actually, he's not that grumpy, but this is what he looked like before the experiment started. He put it on his fridge and had him use it for 2 weeks. And then this is what it looks like after he's been forced to smile every day for getting his food. You can see on the right-hand side, this is him later on. So apparently it works. But anyway, that's a simple example of a effective computing application. As I said, it's a single user application, but it recognizes your emotion. Noni Dipina, who's a famous journalist and VR researcher, she's talked about how VR offers a whole different medium to tell stories that really connect and create an empathic connection. And there are many examples of that. You know, if you want to go and visit the refugee camps in Darfur, you can do that through 360 videos. You can get VR experiences of flying spaceships and fighting monsters and things like that. A nice example is this project called Paint With Me. And this project, a painter painted a picture and recorded her viewpoint with some stereo cameras on her head. And then this was played back later to a second person who was painting and experiencing it in a VR headset. And so they could follow along and get the feeling they're painting with them as well. But the main research focus on my lab is around sharing, and it turns out this is a space that hasn't been well explored in the empathic computing space. Now, can we develop systems that allow us to share what we're seeing, hearing, and especially feeling with others? An example of this, not my work, but work of one of my new PhD students, is called the Empathic Aura. And the idea was to use augmented reality to share emotional experiences across when you have face-to-face communication. So you can see here a person talking with somebody across the table. They're wearing a mixed reality headset, and the person they're talking with has some physiological sensors to measure their emotional state. And when the person in the headset looks at them, they can see this aura floating around their head that shows what their emotional state is. So you can see how people are feeling when you look at them. So that's kind of some of the research that we're trying to do in my lab. I'll give you one more example in a second, but of course, we're all familiar with the technology trends happening in the AR/VR space, and these trends enable us to create new ways to connect with people. So much better advanced displays, real-time space capture, like I've shown before, gesture and eye tracking. And then the thing that we're really interested in is emotion sensing and sharing. And so you can combine AR and VR displays with a wide range of physiological sensors to create emotion mapping. So, and these are now starting to enter the market. On the left-hand side, you can see the HP Omnicept, which has been on sale for about 1.5 years now. It has eye tracking and heart rate sensing in it, pupil dilation measuring, and also has a face camera, so it can measure your face expressions. And on the right is a new display that's going to come on the market later this year from OpenBCI. This is the project Galea. and this has EEG sensors, EMG sensors, EDA sensors, PPG for heart rate, and eye gaze. So across the top of the VR headset, there's 8 EEG sensors, and in the faceplate, there's more EEG sensors and EMG for measuring muscle movement, and EOG for eye movement, and PPG for heart rate. So a lot of different sensors, and combining those sensors together, you can get a lot of information about the person. You can measure, their attention. You can measure their brain activity and use it for neurorehabilitation. You can measure their face expression. You can use EDA to measure their arousal and valence levels, cognitive load, and the like. So that means now we can create VR and AR shared experiences that can tell you a lot about the person you're talking to that you wouldn't normally detect in the real world. As an example of that, one of the areas of research we're doing in my lab is around brain synchronization. So it turned out about 10 or 15 years ago, people discovered that when people were doing activities in the real world, sometimes their brain activities become synchronized. You can see 2 people here who are pointing at each other, and they are wearing EEG brain caps. So when one person starts moving their hand, the second person has to mimic the hand motion and keep pointing at the finger. So what you do is you have, before they do that task, you measure their brain activity, and then they do that task for about a minute, and then they stop and they keep their hands in space like you can see here, and then you measure their brain activity again. And you look for, you measure the phase of the EEG signals to see if they're becoming a synchronization. And so this is a picture of their brain activity before they start. The black dots there show the EEG locations, and the heat map shows the activity. And then this is when they finish. And those arcs appearing now, these show EEG electrodes that are now in sync with each other. And when this happens, people record feeling like they're in a emotionally connected to the other person, or in a state of flow, and feeling more synchronized with the other person. So this is a really interesting phenomenon, and we're curious to see whether we could reproduce the same thing inside VR. And so we were the first ones to look at how we could look at brain synchronization in VR. So you can see here 2 people in VR now. In the VR environment, you can see an avatar across the table with you, and you move your hand around, mapping your hand motion in the real world. And again, we can measure the brain activity, but because this is VR, we can put people into the same body. And so now the people are now both sitting inside the same body. When you look down, you see 2 pairs of hands coming out of your body, and you try and map the hand motion again. And the theory is that by sharing this, the same perceptual cues, you might feel even more synchronized with the person than you do if you're sitting across the table with them. And we found that did indeed happen. So this is the brain synchronization before we started the experiment. The faint lines there show basically noise. And then once we've done that experiment, we measure the brain synchronization again, and we see these dark red lines, which shows a lot more connections between the electrodes that are in sync with each other. So some of the other research we're doing is looking more towards empathic characters. So now we've got the ability to create very realistic virtual characters. This video here is a character from a New Zealand company called Soul Machines, and they can create basically photorealistic characters that, and what Soul Machines does is they build AI, or they build brains for bots. They build the brains that go into these characters. And we can now have the characters recognizing emotional state and respond to that state. So we're looking at how we can build intelligent digital humans that can be expressive and that can recognize your emotional state. And so this lets us build these intelligent virtual agents that go from just being like Siri, which is a speaker representation, to being a 2D character on a screen, to now being embodied in 3D space. This is a video not from our group, but from another research group, showing how this might look in the real world. So here's a virtual character that is walking down the real hallway and sitting on a chair there.
Hello.
And now the person can talk to the character.
Glad you're back. What's up?
And
I would like to know how I can be more healthy.
The interesting thing is, the person moves around, the character
Protein
always
helps build and repair
turns to
muscle,
look at them.
skin-
So in our research, we're trying to also build these empathic virtual mixed reality agents that will be able to recognize your emotional state using sensors like what's on the Galea, and then respond to that as well. So it's kind of an evolution in digital character technology. And the last thing I want to talk about is how this kind of pulls all together. So I've talked a little bit about different advanced technologies that are being combined. And what we can do is combine this together into what you might call empathic teleexistence. And the idea with empathic teleexistence is moving remote collaborators from being observers to being active participants, changing the nature of communication from explicit communication where you're always telling the person what you're going to do to implicit where they know what you're going to do. And this idea of experiential collaboration, of doing things together. And this has been researched for a while in other spaces, and particularly in robotics. They've done work in empathic teleexistence, where you can put a VR system on and feel like you're inside a robot body and interact remotely by doing that. In fact, there's this really bad movie that came out about 10 years ago called Surrogates. And in this movie, the premise was that in the future, we'll all have inexpensive robots, and the robots would go out and do things in the real world that are dangerous, but we'll be able to experience that in our VR system. So here's Bruce Willis going into his VR system, and now he's going into the Bruce Willis robot. Here's the Bruce Willis robot. You can tell the difference because the Bruce Willis robot has hair, and then this robot can go out into the real world and do different dangerous and exciting things, like this guy here is jumping off a building and the like. And of course, it's completely safe. But in this movie, for the first time, people start killing the robots, and somehow that also starts killing people in the real world. And so it's Bruce Willis is this detective who has to figure out what's happening. It's a really bad movie, but the premise is kind of interesting. And actually, this is now becoming real. There's a company in Japan called Teleexistence that are marketing this for real now. So this company allows you to browse through a number of locations. You can put your VR system on, and then you can virtually go to that location, and there you are in a robot body. And now you can experience remotely. This guy's in Hawaii, and he wants to surf, go to a surf shop and buy a surfboard. And so here's his robot. He's got a virtual hand or real hand, so he can touch the surfboard, and through his haptic sensors in VR, he can feel that sense of touch, and take a selfie. And then he can go with his son, and now they're going to go to different locations. So they just jump into VR and go to now to the cherry blossoms in Kyoto. So this is a product you can use now, and it's of course the robots are really super expensive, but their business model is that you don't buy the robot, you buy time on the robot, so you can jump into this location and experience remotely. So this brings me to the end. So basically, the idea of empathic computing is that it allows you to combine elements from all pieces of the metaverse, and it can transform collaboration by doing that, from being an observer to a participant, and by supporting this implicit communication. And in that way, deliver the entire metaverse, going beyond just what people are doing today, mostly focusing on social VR, to combining AR and VR and mirror world elements and the like into this whole thing. So I've talked a little bit today about communication trends, about empathic computing, about research directions. There's a couple of very important areas of research that I haven't touched on that I think is vital. One of them is around social acceptance. It turns out people don't like wearing things on their head and don't want to look silly. And the acceptance of this technology is really more about social issues than technical issues. So there needs to be a lot more study in that area. And there's also huge ethical issues that are raised as well. You know, if I'm using Oculus Quest in my home, and with the Quest sensors, they can scan the contents of my home and use that to build a tracking map, that's great. But where is that model of my home going? Is it just existing on the Quest display? Is it being shared through the cloud to somebody else? So there's big privacy concerns around that. And of course, once you start measuring people's brain activity and sharing that with others and sharing their emotional state, there's huge ethical concerns around that as well. So there's a lot of research questions that this type of research raises. And of course, I didn't do any of this work myself. I should really thank all of my lab. I have a lab of about 35 people that crosses over between Australia and New Zealand. And we also have a virtual intern program. If any of you are interested in technologies like this, you can come and do an internship in my lab without ever leaving Seattle and do research with this. And so we'd love to have you join us as well. So thank you very much for your time. Here's my contact details, the website with a lot more projects on it, my email address, and my Twitter feed for you to follow me. And I'm happy to take some questions now.
Fantastic. Thank you so much. Before we do questions, just because I know we are at 11, I want to give a huge round of applause to everyone who wants to show it, emotes, turn your mic on, whatever you want to do. Thank you so much, Mark, for that talk. That was amazing.
No problem.
in the way that you've seen, because you've done so much work in this on how people kind of perceive each other and have these kinds of shared experiences, did you have any observations or any research about like how the avatars people actually embodied impacted that type of collaboration or that kind of sense of perception of being together?
Oh, there's a huge amount of work in that space, and I've published several papers, but didn't have time to talk about them today. But yes, the avatar representation is really, really important. Those of you who've used social VR experiences, the old avatars were pretty much cartoons with unmoving eyes and unmoving mouths, and not very realistic at all. The current generation of avatars, have mouth movement, which is great. Some of them have eye movement, which is good. And we're getting to the point now where we can have face expression movement with some of the new displays. So that's, of course, those non-verbal cues convey huge amounts of emotion. And so that means we get much richer experiences. Interesting research challenge around that is what happens when you're not represented as a human-like avatar. If you want to represent yourself as an insect or an animal or a robot or something else, then how do people associate emotion with that? And that's been an area that hasn't been well explored. But I think what you've seen is that, when I first started doing VR, our avatars are rectangular blocks with a floating cylinder for the hand, and there was virtually no communication happening apart from verbal communication, and we saw virtually no impact of the avatar. And now having human-like avatars that have really rich communication means we can feel a lot more as non-verbal communication cues, and we can be able to have that same rich sense of interaction you do in the face-to-face settings. But we want to be able to move beyond that, and so that's when the sensors come to play. What happens when you can use a heart rate sensor to measure somebody's heart rate and show that in some way, or the person's emotional state, and you can now measure emotional or communication cues that aren't readily perceptible in the real world. I think that's going to lead to a lot of very interesting collaborative systems in the future.
That's a really good point. Yeah, thank you.
Thanks for the great talk. It's super interesting. I have a question regarding measuring the emotional state. I imagine there are many different data sources or modalities, including spoken words or like facial expression, or even maybe ECG signals. I'm not entirely sure what exactly they are, but I wonder how well does the measuring work, and also like where does the kind of the information come from, like which source does it come from the most, and also how do you kind of learn from multiple modalities efficiently?
That's a really great question, and I would say it's a really, really active area of research. So it turns out emotion recognition has been studied for a while, and people in the psychology field especially have well-defined data sets of video and images that can trigger emotions. So if you want to show people pictures that make them feel unhappy or angry, then there are data sets of that. And a lot of people have done research where they will show those data to people and will measure heart rate or brain activity and use that to make inferences about emotional state. And so that's and in those cases you can measure emotion relatively well. One of my PhD students is looking at the combination of EEG and FNIRS, which is measuring blood activity in the brain, and using machine learning and using those same images and videos to trigger emotion. And he's getting recognition rates in the mid 90 percentile. So that's great. But the problem is that none of those systems are designed for collaboration. So when one of my other PhD students, she was interested in measuring people's emotional state in real conversation. So she had she set up a scenario where somebody was having a conversation with you, and the person having a conversation was asking questions deliberately designed to trigger emotion. So for example, can you tell me about when you fell in love with your partner, or can you tell me about a time that you felt really scared? And she couldn't find any examples of data sets of people who've done that before. And it turns out when you start interacting with people and having a conversation, then things like face expression changes, of course, a lot because you're talking. And so some of those previous measures of emotional state didn't work. And so emotion recognition in that situation is quite poor, down to 70 percentile or lower. So when we start looking at emotion recognition in these social VR and social AR settings, that's where a lot of research needs to be done, and we don't have those data sets we can build from, and we don't even have examples of content that will trigger emotion in those sets as well. So I'd say it's a very, very active area of research.
You were just talking a bit about like collaborative settings and understanding and reading emotional levels. And I noticed that there is a lot of focus on looking at like aspects in facial recognition and such for determining emotional levels. But has there been much research into looking at body language, especially in those collaborative settings, and like how two people interact? I know that might be harder because like you'd probably need more sensors to pick up different readings, but yeah.
Oh, we're not doing work in that space, but definitely there is. There's been some very interesting work done on motion capture and being able to show people data sets of motion captured people, and then from that you can detect if the person's feeling happy or sad. You know, there's often a common phrase, we walk with a spring in their step when they're happy, and it turns out you can tell that. So if people are walking and they're feeling happy, you can measure emotion to some extent from their movement behavior. It's complicated because there's a lot of cultural differences in how people move and non-verbal behavior and the like. But it turns out you don't need a lot of sensors to measure body motion, for example. So some people are starting to do that as well. We haven't done work in our lab on that yet, but we may in the future. Most of our work's been on, to some extent, facial expression, but mostly physiological states, so heart rate, EEG, and GSR, so things like that. That's mostly because you know, in many VR environments, or you're not moving around a lot, in case you're sitting down or standing without much movement, you don't run a lot in VR because you've only got a limited range you can interact in. So we focus on those areas instead. But it's definitely a very active area of research, and you can do it.
Thanks.
I had a follow-up question on collaborative AR. So thank you, Mark, again for the awesome presentation. And I think throughout the years, we've seen like numerous improvements on collaborative AR experience, right? You can make your avatar looks more realistic. You can highlight or adding more signal, either biological or in your gaze signal. So I guess my question is, throughout the years, like what aspect in this AR collaboration have you seen brings up the most, I guess, improvement in how people actually collaborate in AR? You know, just if we're comparing collaborative AR experience nowadays with like 20 years ago, what are the things you see that improve a lot, and what are some of the gaps you've seen that still need more work on?
Yeah, thanks for that. So I think one of the areas that I'm really excited about is using AR for collaboration on remote tasks, especially physical tasks. You can imagine the simple example, you know, if my car broke down and I want to have somebody give me an opinion, maybe I could use an AR display to share a view of my car engine with a remote mechanic expert who could then guide me through what's happening with my car. So that's been an example application he's worked on in one way or other for about 20 years. And in that case, the key parts of that are being able to share a view of your environment and to make the remote person feel like they're really there. And I showed examples in my talk of, you know, how I've gone from 2D video to now 3D captured. But it's really important to enable the remote person to also be able to interact in your space. So being able to have the remote person be able to point or draw in your space. And in those types of examples, you know, you don't really need to see the avatar of the remote person. If I'm talking with a mechanic about my car, I don't really care about seeing his face. All I want him to do is point at the thing in my car I need to look at to fix. So having that remote sense of pointing and that shared awareness is super important. And that same application of remote collaboration on the physical tasks has really become quite an important one in the industry. If you look at companies that are selling AR products, so Microsoft with the HoloLens, they produce the Microsoft Remote Assist, which does exactly that, basically brings Skype into the real world, but enables you to have remote pointing and scene sharing. And a number of other companies are developing similar products. One of the main limitations with those current systems is that the remote person only has a limited view of your real space. And so that's, as with our research, we're looking at how we can capture and share your surroundings. But there are no systems on the market right now that use 360 video or use scene sharing to be able to do that. And so I think that's the next evolution. And I think there's huge commercial opportunity in that space. We didn't, in the old days, if you had a printing press and the printing press broke down, then sometimes the manufacturer would fly somebody to your location to help fix that printing press. When I was in Seattle as a PhD student, we did a little bit of work with the people from the naval base. I think it was in Everett. They had minesweepers, and they told an example of how minesweepers have very complicated technology on them. And they gave an example of one case where there was a minesweeper in the Middle East, and something went wrong, and they tried to figure out what was happening using radio, and they couldn't do that. So they flew somebody out from Seattle to the Middle East to look at what the problem was, and it turned out there was a few switches somebody hadn't turned on this control console. And so this 20 or 30 hours of flying to get the person there, and it was a 5-minute fix. So hugely expensive and wasteful. But using AR technology, you don't have to. They could have. In fact, we built a system for them where they could share the view of the real world and have the remote person in Everett communicate that. So that's an area I'm really excited about, and I think there's a lot of commercial opportunities in that space. But there's still, they have to share not only the view of the 2D view of the person's environment, but also the 3D space. So I think if you wanted to develop or work in a space with lots of commercial potential, then there's potential there.
Thank you.
And if any of this research is interesting to any of you, like I said before, we do have our virtual intern program, so you can come and work on the projects without ever leaving in Seattle. It was an internship at the University of Washington that got me started on my whole PhD career and put me where I am today. So we're hoping to return the favor to people.
Well, there's no more questions right now. As Mark said, you can always contact him over email. Find him on Twitter, I guess. But thank you everyone for attending today, and thank you one last time, Mark, so much for joining us. I know it was a big ask to have you be up this early in the morning for us.
No problem.
For you.
No problem.
So really appreciate it. Fantastic talk again. To everyone here, have a good rest of your week.
Great. Thanks a lot.